write a table like this. We can write all the paths with the starting node, end node, and the weight. So we can easily write a table like this. And then, for these ones, for the starting nodes, we can assign it to a row vector for the starting node. 1, 1, 2, 2, and 3, 3. We can write it as a vector. We call it vector I1, which is composed with all the elements in any order. We can do it like this to compose it as a vector. And then we have I2 as another vector, which has the end node to each path as another vector. And then we have the weight as another vector. Just to do it like this, just ignore this part, ignore the end here. So we can just list the starting nodes in vector A and end nodes in vector B, and then the weight in vector W. And then we can use a sparse command to create a matrix with A, B, and W. We can create a matrix with this sparse matrix. And we can, if you are not that happy with the sparse matrix, you can use a for command to convert it to a normal matrix. So in this way, we can easily describe the graph with a matrix. However, it should be noted that, let's go back to the table again. The maximum number of the end node is 9, right? This is 9. And the maximum start node is 8. So the matrix that's created is 8 by 9 matrix, not a square matrix. And I'll show that through example later on. And for this particular matrix, for this particular map, graph, we can create 3 vectors, A, B, and W. And we can use commands like this. Sorry, is it okay with this part? I'm quite certain. Oh, sorry. Here. We can establish the 3 vectors. And then we can use a command R equals to sparse AB, BB, W. And this is a matrix, but it is not in a familiar form. So sometimes we can rewrite it in a standard matrix format. So this is a matrix to describe the map. If you check the size of the matrix, you may find that it is an 8 by 9 matrix, because the maximum number of the initial point, starting node is 8, and the maximum node number for the ending node is 9. So it is 8 by 9 matrix. And this kind of matrix is not quite good in representation, in the matrix representation. We need a square matrix. So we have to use a command like this to extend the original matrix into a 9 by 9 matrix with the last element in the matrix 0. We can extend it to a 9 by 9 matrix. So we can use this matrix to uniquely describe the original map or the original graph. And now, there are two ways to solve the shortest path problem. One is by they call it bioinformatics toolbox, which is a very new one. It's new versions of Matlab. And you can use this toolbox to solve this kind of problem. And in this toolbox, there are a few functions to be used. One is to display, to create a graph object, and you can also display it graphically using this command. And then use this command to find the shortest path. And finally, you can use view command to show graphically the shortest path, solution to the shortest path problem. I'm not quite sure whether you have this toolbox on your computer, so let's try it first as a demonstration. So we have created a matrix R already, which is a 9 by 9 matrix. And then we can use a command view to display the original problem automatically. So this is the graph they generated automatically with the command. We have from node 1 to node 9. And now the problem is, what is the shortest path? So this is the first step, how to create and draw the map automatically. Once we have defined the R matrix, then we can use a command like this to find the shortest path. And the command is code like this. This is the R matrix which describes the map itself, and this is the starting node, and this is the end node. And by coding the function, R should be a sparse matrix. We have to convert it into sparse matrix again, like this. So D is the minimum time required from node 1 to node 9, and this is the path in sequence from node 1 to 3 to 4 to 5, and then to 7 to 9. So this is the final solution to the problem. How can we display it graphically? Again, we have to use the bioinformatics toolbox. I will explain it later to you, the commands. And these are the results. From 1 to 3, 4, 5, 7, 9. It is exactly the same as the one we obtained using command. And let's check details of the commands. The command I used here, the first command here, is to set the node on the path. Set it to something like a red color. These are the components of RGB. R is 1 and this is G and B. So it's nearly a red one. And then we can find all the edges and set the edges on the path, on the shortest path. Also set the line color to white color. So this is the final result we get.